and welcome back to the next video of electrostatics. So as discussed earlier in the previous video, we have discussed about the axial electric field. So in this particular video, we'll be discussing about the equatorial electric field. That is the field lying anywhere except the line joining the two charges. So in this case, we are finding out the electric field at a point P, which is at a distance x from the center of the dipole. As I have already mentioned, the distances are always measured from the center of the dipole. So the point P is at a distance of under root e square plus x square from both of the two charges, as you can see from the figure. It's very clear, right? So first of all, in order to get the total electric field at point P, we need to find out the individual fields for charge 1 and the charge 2. So for the first charge, the electric field E1 is given by kq1 by r1 square, which will come out as kq by x square plus e square. Similarly, since the second charge is also at the same distance, it would come out to be kq by a square plus x square. These distances are being found out by using the Pythagoras theorem, so that's pretty simple. Now, in this case, if we need to find out the net field, you can see both of the fields E1 and E2, they are making a particular angle between them. Okay, they are not in the same direction, neither they are in the opposite direction. So we cannot directly add or subtract the fields in order to get the total field. In this case, we need to either go by vector addition, that is the resultant, or by vector resolution. But I would like to say you, vector resolution is an easier technique to get the answers in a pretty simple time. Okay, so in this case, suppose if I go by vector resolution, how am I going to solve it out? So, since E1 and E2 are the two fields, let me consider this angle to be theta. So if this angle is theta, so this angle would also turn out to be theta. Okay, so if I resolve E1 first of all, E1 cos theta would lie in this particular line, and E2 sin theta would lie in the y-axis. Similarly, if we are going to resolve E2 is going to fall in the x direction as E2 cos component, and the y component would be in the negative y-axis, that would be E2 sin theta. Okay, so these are the resolved vectors of E1 and E2. Now you can see, since E1 and E2 are magnitudinally same, so E1 sin theta and E2 sin theta being exactly in opposite direction, they would cancel out each other, right? So the only remaining or only surviving fields that we are having is E1 cos theta and E2 cos theta, and both of them are in the same direction, that is in the right hand direction. So in order to get the net field at this point P, all we need to do is we need to add up E1 cos theta and E2 cos theta. So E net, which is the equatorial field finally, that is EP, will be given by E1 cos theta plus E2 cos theta. Since they are magnitudinally same, I have written that to be E, so I can write it as twice E cos theta, where these are simply taken as E. Okay, so if you substitute the magnitude, or if you substitute the values from the formula, you'll get it as 2kq by a square plus x square cos of theta. So if you apply trigonometric ratio in this particular triangle, if you find out cos of theta, that is base by hypotenuse, you will get it as a by under root x square plus a square. Substituting those values here, and also we know that P is given by charge multiplied by distance. Here as well, we have taken the distance between the two charges to be twice a. So your dipole moment P would be given by 2aq. Hence, 2aq was replaced by P, and we will get the formula as kp by a square plus x square whole to the power 3 by 2. Now, taking some assumption into consideration, we can solve this formula further, which will look down as. So solving the formula further, as I said, kp by a square plus x square whole to the power 3 by 2. If I take an assumption for x to be much larger than a, then x square plus a square can be nearly considered to be x square. Hence, the formula would reduce down as kp by x cube. Now, this is the formula for E equatorial. But you also need to know the directions and the sign conventions, as I say. So, here you can see the net dipole moment P, that is always directed from the negative charge towards the positive charge. Hence, the dipole moment P would be in this particular direction, that is in the left direction. But the net electric field that we got, it was in the positive x direction, because E1 cos theta and E2 cos theta both were in x direction. So, since the net field E net is in the opposite direction of the dipole moment, hence there should be a minus sign along with it. So, this minus sign only represents that the net equatorial field is always in the opposite direction to the net dipole moment. So, that is all you need to know about the equatorial field. Thank you.